All right, in the last lesson we looked at Thomson's plum pudding model, and we know that he was the first to sort of determine the existence of negatively charged electrons as being separate from the positive parts of the atom, but he never really came up with a decent model other than the whole plum pudding type of thing. We also know that Millikan did the oil droplet experiment, and what importance of that is he actually figured out that the oil droplet was in multiples of 1.6 to the negative 19. So remember, he had a glop of oil, he would balance the electric force with gravity, and from that he found that the charge on those things were always some multiple of 1.6 to the negative 19. The smallest one was exactly that, the elementary charge. Other ones would be 2, 3, 4, 10 times, whatever, bigger than that. So he was sort of key to sort of figure out what the elementary charge is, and the idea that it was quantized. It was in multiples of that amount, not just any kind of random decimal. So with Millikan's advancements and what Thomson did for charge to mass ratio, if we now know the charge of electron is 1.6 to the negative 19, we can put those two together and determine that the calculation of an electron then is 9.11 to the negative 31. So that number is a calculated mass. It's obviously not measured by hand. But using the Thomson and the Millikan ideas, put them together, we can actually know the mass of an electron now. So the next guy that comes along that fine-tunes the model idea is Ernest Rutherford. And he was actually doing experiments with alpha particles, which are just the helium nucleuses, and we're going to get to those later on in a future topic. But he basically would use a radioactive sample inside of a lead box, so the lead kept it from emitting outside the box, but he had a small hole drilled in it so that all of the alpha particles would then be emitted outside of that hole. And he would shoot it at various materials. And the one he found got good results was when he shot it at a thin sheet of gold foil. So kind of picture it like aluminum foil that you'd have in your house, but it's made of gold. So gold is pretty thin. You can get it really thin into a foil, and we know it's fairly dense particles in terms of its number of protons and so on. So basically the alpha particles being shot at the gold foil, he found some really strange results. So once they hit the gold foil, then he could see what path the alpha particles were going through. So what he ended up concluding was, let's go back to the other diagram. So there's basically three results happen. The alpha particle hit the gold foil and bounced straight back. That was one option. Or it hit the gold foil and just basically went straight through was the second option. Or it hit the gold foil and it was deflected at some sort of angle. So you got different kinds of angles, being straight through or bouncing completely straight back. So he was pretty surprised by the results, and he was trying to figure out what was going on. So using Thomson's idea, he thought that if it missed the electrons, then that would have been the case where it went straight through. So the electrons were spaced out enough that the alpha particle just went right through the space between the electrons and nothing changed. But he also figured out that if they hit the electron, he thought then it's kind of like the Compton effect, where the wave, the alpha particle coming in, gets scattered at some sort of angle and the electron goes off at the other angle. So he used that sort of idea to say, well, okay, when the gold alpha particle is hitting the electron of the gold, then it's getting scattered. And the third one was the one that was the strangest. He found that some of the alpha particles hit the gold foil and bounced perfectly straight back. And he thought that was pretty strange, because he goes, that would be like having a 15-inch shell, so like a cannon or a big tank bullet, hitting a piece of toilet paper and bouncing straight back. So he thought that was pretty strange. So what he then concluded was, well, if the alpha particle is hitting something massive, that would be reason for it to bounce back. And if we know the alpha particle was 2 protons and 2 neutrons, then so we have like 4 particles, and gold on our periodic table is quite a bit bigger. It is, let me just find it here. It is 79 on the periodic table, so that means, so it's hitting gold nucleuses, which have 79 protons and 79 neutrons, so obviously way bigger, so that does make sense that this smaller one has way less momentum, so it's just going to bounce perfectly straight back when they collide. So because of this, then he basically predicted based on the probabilities that it hit. He thought then that the nucleus, most of the mass is in the nucleus and the electrons are just orbiting around. So if he said if the alpha particle went straight through, it went through and missed everything. If it hit the nucleus, that's where it would bounce straight back. And if it hit an electron, that's when it would deflect off at an angle. So that's why he was getting the three different results. And Rutherford's model is still accepted. He accepted Thomson's ideas, but he just sort of said that it's no longer just a positive mass fluid, it's actually a positive nucleus at the center. And he sort of used planets orbiting the Earth as an analogy, and that's how he came up with his model. But as soon as he published it, there were some flaws to it. He thought they were just orbiting around in circles. But if they're moving in circles, that means they have to be accelerating. And if they're accelerating, when we have accelerating charge, we know that from Maxwell, we said that'll create EMR. And if you're creating EMR, that means it's going to release some energy. And if it releases energy, it's going to slow down, and those electrons would eventually crash. So if you had a positive nucleus and you have this electron in orbit, and if it's going to slow down by losing energy, we know that it would eventually collapse in on itself if it gets slower and slower, and eventually it would collapse. This doesn't happen. Our atoms are quite stable, so there's got to be a problem. So what's the reasoning? What's the right model then? That's to be determined. So we'll stop there, and we'll look at Bohr's model next.